This conference will now be recorded.
Very good evening, students. Yesterday we had started magnetic effect of current and we had discussed the Biot-Savart law and its application. As you know, Biot-Savart law will help you to find out magnetic field due to current carrying wire that may be infinitely long or finite. So the Biot-Savart law, the statement of the Biot-Savart law is this: if I write in terms of like numerically, if we write Biot-Savart's law, vectorially we'll write dB is equal to mu0 by 4 pi I dl cross r by r cube. So this is the vector form of Biot-Savart law, and you can see this. So this quantity, this cross product is a vector quantity, so the magnetic field is vector quantity. And see the scalar form of this equation will be dl sine theta divided by r square. And see, actually I can draw this current element. So at certain point P, we're calculating magnetic field due to this element. So this is R, this is actually R, and this direction is the direction of dl, and angle between them is actually theta. Okay, anyway, we had discussed that. I'm just writing the formula, kind of formula. Okay, so this was general formula for our general form of Biot-Savart's law. Then we had discussed magnetic field due to a straight finite current carrying conductor yesterday. Okay, so this particular part I have to keep here. Let me keep this here. Okay, so we had yesterday discussed about magnetic field, like application of Biot-Savart law, magnetic field due to a straight finite current carrying conductor. And see, this is the conductor. Okay, current carrying conductor. So this conductor is carrying a current I. Okay, in this direction, upward direction, as you see, and we have to calculate magnetic field at P due to this current carrying conductor. So for that we had just considered one element. Okay, one element, and then you used this thing, this general formula, to find out the particular formula for this particular straight current carrying conductor. And you know the magnetic field obtained from straight current carrying conductor will be mu0. Suppose this is A, this distance PQ is A, mu0 I by 4 pi A sine phi 1 plus sine phi 2. Okay, let me write it down so that I can get some more space. Okay, we'll write it here. So the magnetic field, magnitude of the magnetic field, what we got, mu0 I by 4 pi A, and this is sine phi 1 plus sine phi 2. So this is the formula we have found out yesterday. Now we'll try to see some special cases out of that. Yesterday we rushed into this. So this is actually kind of an kind of a general formula for state conductor. Now we can, and also this is for finite one, obviously we can just convert that for infinite one. Okay, so general formula for a state conductor we had got mu 0 I by 4 pi a sine pi 1 or theta 1. In this case theta is given, so we'll write theta sine theta 2. Okay, so this is the general formula. Suppose I have the current carrying conductor infinitely long both sides. Then look, this angle, see the angle we calculate phi 1 and phi 2 or theta 1 theta 2, whatever you say, from this baseline, this is called base or reference line, to upward direction will be positive phi 2, and this side we take negative phi 1. Okay, this angle. So this is the calculation of angle. So now see, if the wire is infinite, then both theta 1 and theta 2 will be 90 degree, and the formula actually reduces to this mu 0 I by 2 pi a. That means, okay, so this is mu 0 I by 2 pi a, and you can see this is B is magnetic field at a distance. Okay, it is inversely proportional to the distance, inversely proportional to the distance between the current conductor and the point of observation where we are seeing the magnetic field or calculating the magnetic field. So it is inversely proportional. It is same as okay, we'll see later. And this, see this case also the wire is infinite. So this is infinite wire, but the point of observation is at one end of the wire. So in that case, you know what will happen. One side it will be 0 degree. See this angle, see phi 2 will be, in this case theta 2 is 0 degree, nothing is there here. Okay, and whereas theta 1 is 90 degree. So in this case theta 1 90 degree means 1, so this will be 0 anyway. Mu 0 I by 4 pi a, or I can write half into mu 0 I by 2a, or this is actually due to infinite wire, we can keep this value of magnetic field for an infinite wire to be the standard one, mu 0 I by 2 pi a. And see, this is when the point of observation on the point where we are calculating magnetic field is at one of the end of the conducting wire, then the magnetic field will be half of that. Half of the original infinite wire. Okay, now one more point is that here, see, if suppose this point of observation M is situated exactly on the perpendicular bisector, then this theta 1 and theta 2 are same. Okay, so for that case we get mu 0 I by 4 pi a sine theta 2 sine theta. Now this sine theta could be, if it is finite in length, then it could be see this is y by 2, so y by 2 sine theta I have to find out, right? So y by 2 perpendicular by this length. Okay, again this length we can find out. Okay, this is a y by 2, so y square by 4 plus a square. So 4a square by plus y square by 4 by 2. So 2 gets cancelled actually. Okay, so this is the formula when this is on the perpendicular bisector. Okay, so we have got the formula. Now today first let us apply this formula for solving some numerical problem. So we'll be applying this formula. See the main formula we got for a straight conducting wire, mu0 I by 4 pi a sin theta 1 plus sin theta 2. This is the main formula or master formula for a straight conducting wire. Now see, we have to calculate the magnetic field at the center of a coil of a form of square of side 2a. Okay, current I. I have to calculate magnetic field due to a square. Like I had a wire which I bent to form a square of side 2a. The thing is something like this. See, the conductor is bent to a square and each side is having the same length 2a. Okay, same length 2a. That's why it is square. Anyway, and now what we need to do, we need to find out the magnetic field at the center of the square. As you see here, this is the center. Now this is the current. I can just take one by one. I can take this current AD, current carrying wire. Okay, due to this at the center, okay, O is given. At the center O, what will be the magnetic field? We can calculate using this formula. See here, if I draw a perpendicular bisector to this side, then this will be A, this side will be A anyway. And this angle, since these are 45 degrees, these are 45 degrees, so this is 90 degrees, so this will be obviously 45 degree. So both the angles are 45 degrees, so I can say theta 1 and theta 2 are 45 degree. This is just by observation. Both are actually 45 degree. Now what is this A? A is the distance. What was there? This was R there. So 2 pi A. So we will just apply here. Sin theta 1, theta 2 we have got. This is 4 pi A. A is this side actually. And we know how to calculate the angle. Okay, so look here, then what we get? Mu0 I by 4 pi A. Okay, so this is 945 degree. Sorry, sine 45 degree. This is sine 45 degree. That will be 1 by 2 by root 2 actually. So here, look, this is mu0 I by 4 pi A. 1 by root 2, 1 by root 2. So 2 by root 2. And now root 2 can be cancelled with this. Okay. So we get mu0 I. So what we are getting here, So this is actually mu0 I by 4 pi root 2 pi by sorry, this is 4 pi. A I have to write for this problem. This is A only. 1 by root 2, 1 by root 2, so 2 by root 2. This is the way. Now, this is for only one arm. If I have to calculate magnetic field due to other arms, there are 4 arms, and at the center, we have to calculate the magnetic field. And as you know, magnetic field is actually following superposition principle, then we can add them up. So this is for only one. I have to multiply 4 with that. So we have to multiply 4 with that, and then we get magnetic field. Just a minute. So this will be the magnetic field at the center of the square of radius, sorry, square of side L is equal to pi by 2. I'm sorry. Okay, we'll go to the next page, like next problem. So this is done. Now we have to calculate the magnetic field for a current of 1 ampere flowing in the sides of an equilateral triangle. So here the example number 2 says that a current of 1 ampere is flowing in the sides of equilateral triangle 4.5, triangle of side 4.5 meter. Find the magnetic field at the centroid of the triangle. So for that, how to approach, we'll discuss. So here also we need to first find out the, we need to remember first of all the formula sin theta 1 plus sin theta 2, because each side of the triangle is actually a straight conducting wire. So that is what will be applicable, like we can use. Okay, so we'll use that. So here, see, let us consider this side AB. So to solve this problem, as you know, we had to find out, see, we have to find out the magnetic field at the centroid, it said. So we have to find out the distance, first of all. So this distance, what is this A in this case? L is given. So what is the CP or PC length? This is the height of the equilateral. This is actually equilateral triangle. So root 3 by 2 into L. This will be height. Now what will be OP? OP will be actually, see, this length will be divided 2 is to 3. Sorry, 2 is to 1 ratio. So this part will be 2 by 3 and this part will be 1 by 3. So 1 by 3. Okay, so that means L by 2 root 3. So this is actually OP, this part. Okay, this part is OP. Now see, since it is equilateral triangle, this will be 60 and these are perpendicular bisector. So this is 30, 30. So this is 90. So this will be theta 1, theta 2, both will be actually 60 degree. Okay. Now we have got sin theta 1 and sin theta 2. See, theta 1 and theta 2 we have got. We can actually put those values and see all the values are known now. So if we apply, see, b is equal to mu 0 I. So I have to find out this part. This part 60 degree, 60 degree. Okay, so sin theta 1 and sin theta 2. So these are actually values of 60 degrees. 60 degrees. This is also 60 degree. Okay, so this part is done. mu 0 I by 4 pi. Let this be here. See, 1 by A, what we are getting? A means OP. OP we have got this. So then 1 by A will be 2 root 3 by L. Sorry, this is not here. 60 degree means root 3 by 2. This is also root 3 by 2. So 2 into root 3 by 2. Okay. And then in place of A, we have to put this L by 2 root 3. L by 2 root 3. This gone. So mu 0 I by 4 pi L, this will go to 2 root 3 into 2 root 3 I'm sorry, this is 2 root 3, and here actually root 3. So 2 into 3, 6. Root 3 by 2, root 3 by 2, all right. 6. Okay. So this is 3, 6. So 6 mu 0 I mu 0 I by 4 pi. This is actually magnetic field for. So this is general formula I have already developed. So in this case, so 6 mu 0 I by, so this is for only one side. So I have to multiply 3. Okay. So magnetic field at the centroid for all this will be B at centroid. Okay. All right. We'll go to the next part. So this is for a single side. Okay. Double side is, see, I have 4, sorry, 3. So I have to multiply 3 here. How many? So we have learned Biot-Savart's law for straight conducting wire. Now we'll learn Biot-Savart's law for a circular current carrying loop, and we'll see in that case magnetic field will be existing along the direction of the axis. Okay, along the direction of the axis. So to solve to develop that, let us consider this figure. See, this is a loop, as you see. Okay, so this is a loop. So we are calculating now magnetic field on the axis of a circular current loop. So this is a loop of radius r. As you see, this is radius r, and we have to calculate magnetic field at a distance x. So this point P is at a distance x from the center of the coil, center of the loop, current carrying loop. And okay, so you can see that this loop can be considered as a number of small element, current element of length dl. Okay, so I am just considering now two such element, current element. One is at the top and another one is diametrically opposite to that, that is at the down. Okay. As you know, the current element will always has the direction towards the current, and in this case, in case of car, this will be tangent to that particular point. Okay, that particular element. So tangent to that, as you see here, this is the dl length, direction of dl or current element, and this is the distance from the current element to the point of interest P. So r is the distance from the from the loop, sorry, element of the loop. Now if we just see the direction, see your DL is this direction and R is this direction. R is in this direction. So along which direction the magnetic field will be? Magnetic field will be something like this. So this will be magnetic field line, direction of magnetic field line. Okay, so in this case, see at P, when we are calculating magnetic field due to a particular element, let us say this element, which is at r distance from the point of observation, and this is from center of the ring. This position is at x distance away from the center, and the loop is taken or considered to be vertical. So here magnetic field direction will be this way at this particular point, and let us say that magnetic field is creating phi angle, phi. Therefore this magnetic field could be subdivided into two. So dBy means dB sin theta, sin theta. Okay, so along this way sin theta, and along x direction dBx. So dBx is actually b so dBx. So this, there will be a cos theta component. Okay, cos theta component. Now we have to write so this formula. So mu 0 I dl cross r by r cube. Now what we are going to do, magnetic field, we'll just put the value I, then 4 pi, would put the value of dl. I'm sorry, dl may not be given. Okay, so far it is all right. Now we have to consider this element, this particular element. Then magnetic field, we have seen that that will be actually along the axis. That how do we get that this will be only along the axis? Because see, if I consider another diametrically opposite this, so magnetic field will be along this direction. Okay, this, if this is phi, so this will be along, this will be actually dB cos phi x. So and vertical part will cancel each other. Okay, in both cases that will be cancelling each other. Okay, so okay, so we have got dB cos of phi. So this component we have got twice, so 2 into that. So that will be the ultimate magnetic field. And see, to calculate, see here, actually look here, we'll be ultimately using this formula, general formula mu 0 I by 4 pi. Okay, mu 0 I by 4 pi. Here dl cross r will get actually dl sine theta or sine phi in this case. Let us say sine theta itself. This is r square. So this is actually, see, this angle is 90 degree. This the angle between the element and the position vector of P point. So that will be, see, theta is 90 degree here. So what you get, mu 0 I by 4 pi r square. Okay, and we have to see now. We have got the magnetic field due to this ring, at least for the two element. We have got dBx is equal to 2 into mu 0 I by 4 pi r square into cos phi. So this is the formula. Okay, so we have to find out what is cos phi. See, if this is phi, this is actually, this is 90 minus phi, 90 minus phi, and this also will be 90 minus phi. This is 90 minus phi. This particular angle will be 90 minus phi. Okay, so if we find out what is cos phi, see, I can write cos of phi means sine of 90 minus phi. So sine of 90 minus phi, sine means perpendicular by hypotenuse. Okay, r by r. So this small r can be written again. Okay, let us first write cos phi means how much. Okay, so for the time being, let us take for a single one itself, cos phi. This gets me mu 0 I by 4 pi cos phi is this x by r. Okay, I'm sorry, this is x is actually, this is r by x. Sorry, that is also not true. Perpendicular r by smaller. All right, this is fine. Okay, so far it is all right. Now we have to put the value of cos phi. Cos phi we have got r by r. That means mu 0 I r by 4 pi r cube. Okay, 4 pi r cube, and this is for, say, this is for single one, db x. Now if we want to calculate the total magnetic field due to this ring, dbx integration dbx is equal to, I think there was the dl term was there, which I have missed already. Dl term will be there. So here we have got, so mu 0 I by 4 pi r square. Then this is r square, sorry, r dl by r cube. Okay. So this r cube, small r cube, we can express in terms of x and r. Okay. So small r is actually r square plus x square, root over of that. That means we can, I'm sorry, this is again the same thing. So mu 0 I 4 pi, and see this r will be anyway out. If we do the integration, this is r cube means x square plus r square whole to the power 3. So this dl, integration dl will be giving you 2 pi, mu 0 I r by 2 pi 4 pi x square plus, so mu 0 I by 2 pi, so 2 2 and pi get cancelled. So mu 0 I by, so mu 0 I so here 2 will be cancelled, so mu 0 I by 2 into, this is, I think that should be r square. Okay, let me just check. So x square is here, this is, this will be, this will be x square. Okay, this will be 3 by 2 actually, 3 by 2, 3 by 2. Okay, so one more thing will be there. So this will be r square. Okay, so 2 pi r will be getting 2 pi r, not 2 pi. So that's why it will come as r square. Okay, 2 pi r, 1 r is here. So this is how we look here. Magnetic field mu 0 I by 2 pi. This is r square. R square divided by 2 into, sorry, this 2 pi will not be there. mu 0 by 2. R square by x square plus r square whole to the power 3 by 2. Okay, this is mu 0 I by 2. So if there are n number of turns, say, then in case of n number of turns, we get mu 0 I by 2 pi n r square this is r square here and whole to the power 3 by 2. Okay, so for this n number of turns, that will be like that. Formula has to be modified. Now we'll have some special cases in the discussion. Let us see the special cases of the formula. See, we have got what we have got. Suppose I have current carrying loop. I have a current carrying loop of radius r, and I have to calculate magnetic field at any point, axial point, which is at x distance away, say this one. Okay, and I can consider first one element. With respect to that, we can do the calculation part, and finally we have to integrate it. We see that magnetic field will be along the, if this is x-axis, okay, if this is x-axis, bx. So what is the magnetic field formula for magnetic field at any axial point? We have got the formula for that to be mu 0 I r square by mu 0 I r, okay, 2 into x square plus so here at the center, what will be the magnetic field at the center, and where will be the maximum? Those things we can find out. At the center, what will be the magnetic field? See, at the center, this x will be 0. Okay, so this x distance will be 0 at the center. So what we will get? Mu 0 I r square divided by 2 into this. This is 0. That means you get this only. So this is r cube. So mu 0 I by 2 r. This is at the center. Okay, mu 0 I by 2 into r. Or if there are a number of turns, then we have to multiply the number of turns also. Okay. Now, if this point x is much greater than capital R, then this R can be neglected. So in that case, magnetic field will be along x-axis anyway, mu 0 I r square divided by 2 into, see, I have to just leave this one. Then this is x square. This will be multiplied, so it will be x cube. Sorry, x cube, yes, x cube. So this is the formula. Obviously here, okay, so this is the formula. So we have got magnetic field due to this special case also. Then we have to find out the magnetic field at a point distance equal to the radius of the coil. Distance equal to, so an axial point at a distance equal to the radius of the, see, if the x is equal to r, if this x is equal to r, then I'll put it here. So bx will be x is equal to r. Okay, Okay, so we have to do a small approximation. So we have got magnetic field Bx along this direction is mu 0 I mu 0 I by 2. This is r square divided by r square plus x square. So when x is much greater than r, so in that case Bx mu 0 I by this was actually 3 by 2. So this will be cube and one r square was there, right? One r square was there. 2 r. This is r cube mu 0 I by this into okay. So the final result will be at okay. So this was already done. So we are just seeing at b at x is equal to r. So this is so bx is known to us mu 0 I, okay, mu 0 I r square by 2. So when both are equal, then what will happen? Mu 0 I r square divided by 2 into this will 2r. Let us say 2r. So 2 root 3 by okay. Square will be there. 2 square x square plus x square. The 2x square or 2r square. So this is 2r square. Okay. So this would actually give you mu 0 I this is r square. See, this is r cube. It will be. I'm sorry, this will be r cube. So this will cancel. So mu 0 I by 2 to the power 5 by 2. And this will be r. Okay. So this is the formula again for a distance equal to radius of the circular coil. Okay. So we'll stop it here for today. In the next class, we'll take up various numerical problem on this topic what we have discussed today. Okay. So thank you for your patience. Bye for today.